Hi, so ready to start chapter 5. So this will be the first video for Math 1149, trigonometry. So we're starting chapter 5, which is on trigonometric functions. In the very first section, we're looking at our angles and their measure. And the main part of this section really is just defining a lot of terms and a basis that we'll need and use throughout the course. So the very first objective is to be able to find degree measure. So we start by defining a ray. So a ray is a part of a line that consists of an endpoint and all points on the line to one side of the endpoint, right? So essentially, if I have an endpoint and we take a line, then all the points on this part of the line, right? Essentially, a line has two endpoints, right? So the difference what array is we have some endpoint, and then we cut off, everything that's not. Whoops, didn't mean to erase that. Basically cut off that other side, right? So this red side is what we got rid of, right? So it's essentially a portion of a line, right, where we're cutting off one of the endpoints, right? So if I had like I was drawing, if I had this as an example, where I have an endpoint, and let's name that P. Then we could go this direction, and then let's say another point on this ray is point Q, right? Then this would be ray PQ, and we could show that by drawing PQ and then drawing a ray symbol above it, right? And then, if I had this situation, right, where essentially P and Q are like in the same spot, but the ray is basically going in the opposite direction, right? This would be ray QP, right? So those are not the same, right? So in other words, note that PQ is not equal to QP, right? So the direction does matter, which way it's going, right? And then just another note, we could say that a ray is named using the endpoint and another point on the ray, right? So that's what I was describing in reference to ray PQ or ray QP, right? So, another example of this is if I had this ray, and let's say we have an endpoint of X, another point on here Y, and another point Z, right? Then we could call this ray XY, or we could call this ray XZ, right? So really the important part is, if you notice, the endpoint is always listed first, right, in all of these situations, right? So it's also important to note that we always list the endpoint first, right? So then we need to define a ray, so that way we can talk about an angle, right? So you can see here I have typed up, so an angle is formed by rotating a ray about its endpoint. The starting position of the ray is called the initial side of the angle, and the final position of the ray is called the terminal side, right? So the common endpoint is called the vertex of the angle, and the vertex is often named by a capital letter such as capital A. right? So let me demonstrate this for you, right? So essentially, if I start out with this ray, right, we'll call this ray AB, right? So remember, this is going to be called the initial side, right? That's where we start. And then if you imagine, like at A, it's basically like a fixed point. We can't, that's going to stay there, but I can move the ray then, right? Almost like a hand on a clock, right, if you will. I can rotate this, or rotate it this way. So essentially, we end up with this position. So, and I'm going to call this new point here C, right? Then this would be called the terminal side, right? And then remember this guy, this is the vertex, right? And then it's also common to use a Greek letter for an angle, right? So I could use like Greek letter, like theta if I wanted, right? Oops, that's a weird looking theta. There, right? So this angle A, right? This angle A here, we can rewrite a couple of ways, right? I can call this angle A, right? So this is like an angle symbol, right? I could call this angle BAC. I could call this angle CAB, right? So something to, also I could also call this angle theta, right? So these are 4 different ways that I can name this angle, right? Symbolically, right? So some notes here is that it's important that the vertex is always in the center. When naming, right? So this would be in reference to the second and third way to write that, right? So notice the vertex, right, A, is always written in the center, right? So it goes in order, right? So we're either starting at C and going to B, or B and going to C, right, essentially. And then, as I mentioned, it's also common to use Greek letters to denote angles, right? So we can use like theta, we can use beta, alpha, or gamma, right? And if you're not familiar with your Greek alphabet, right, you can easily just Google, like Greek alphabet and look at some images and see, see what those look like, right? And some people draw the Greek alphabet slightly different, just like some people write, the alphabet we use in the U.S. Write some letters a little differently, but they're all about the same, right? Excuse me. So the next thing that we want to discuss is what we call standard position, right, of an angle. So an angle is in standard position if its vertex is at the origin of the xy plane and its initial side is the positive x-axis, right? So essentially what we want to do is, take like this vertex AB here, and we're going to make this be the x-axis, and then we just, draw the y-axis right through the vertex, right? So this is the positive y, this is the positive x, negative y, and then so we're putting that on the xy plane in this fashion, right? So that would be in standard position, right? So you know, if I want to redraw this, right? So if we just start with an XY plane, right? And then, you know, this would be the vertex. I have my initial side here on the x-axis, and then we'd have something to this effect, right? So this angle we could call, like, let's say alpha, right? Whoops, didn't mean to do that. Right, so just to point some things out, right? So the vertex is at the origin, right, which is at the point 0, 0. And then, you know, this is the initial side on the positive x-axis, right? So then, you know, this side, of course, just to practice, would be called the terminal side, right? So that would be angle alpha, right? So then I have some more definitions here with some fill in the blanks. So we have the measure of an angle quantifies the direction and the amount of rotation from the initial side to the terminal side, right? So we go with direction and also the amount of rotation, right? So the measure of an angle is positive if the rotation is counterclockwise. Oops. Right? So then the measure of an angle is negative if the rotation is clockwise. Right? So remember, clockwise is, you know, the direction of the clock is that would go, right? You know, before digital clocks, right? An analog clock. So there's two units, you know, that we're going to look at to measure an angle. The first one is going to be a degree, right? So one unit with which to measure the angle is the degree, right? We'll also look at radians as well. So you might be familiar with degrees and radians, or probably at least familiar with degrees, and radians might be new for you in this class, just depending on your mathematical background, right? But just some notes that you would know is that, you know, one full rotation is 360 degrees, right? So in other words, you know, 1 degree would equal 1 over 360 of a full rotation, right? So if I took a circle, cut it into 360, you know, equal sectors, right? Then one sector would be 1 degree essentially, right? So we can just practice a few of these, right? Just a few diagrams. So if I draw this situation where we have my vertex at the origin, my initial side's on the x-axis, and then we're going maybe like halfway in between the positive x and y axis, then this degree would measure 45 degrees. Right, so we're in the first quadrant, right? So remember, if we're going counterclockwise, it's a positive degree measure, right? So then if I draw another picture where, you know, the vertex is at the axis, my initial side, you know, is on the positive x-axis still, and then maybe I'm going to go in the negative direction, right, clockwise, and land here, then this would be negative 270 degrees, right? You know, maybe another situation is, you know, having my vertex here. Here's my initial side. Here's my terminal side, and maybe let's not draw on a scale. You know, maybe in between here there's like 30 degrees, right? So that's a positive measurement because I'm going in this direction, right? So notice how I'm drawing like these little arrows showing the direction I'm going, right? Because, you know, this picture, if I didn't draw this diagram, right, I could have also drew, you know, something like this, you know, this red angle here, and that would of course be 90 degrees, right, a right angle. So it's important to draw in these little arrows so we know what's the initial side and what's the terminal side, right? So then, you know, if I draw another XY plane, here's my vertex, there's my initial side, say my terminal side's this way, and we're going from here to here in this direction. So this would be a negative direction, right? I'm going clockwise. So this would be, you know, something like negative 150 degrees roughly, right? So you just want to get familiar with the positive, negative thing, right? So then how to denote the measure of an angle? So let me show you this. Right? So, so how to denote the measure of an angle? So let me just draw a situation in here. So if we have an XY plane, maybe we have an angle theta. Right? Which looks something like this. And let's say this is measures 60 degrees, right? So some ways we can denote this is we can say the measure of angle theta equals 60 degrees, or we can just say that theta equals 60 degrees, right? So when we say this measure of theta, right, we read that as measure of angle theta, right? So when you see a lowercase m and then like a Greek letter inside parentheses, right, that's mean that measure of that angle, right? So either one of those is acceptable, right? So then we have some special types of terms that we use for measures of an angle, right? And I used some of them, and many of these you probably heard before, but just to make sure we're on the same page. So if I have a situation like this, where my terminal side looks like this on the y-axis, right? Sometimes we might draw like box that off, right? So here's the angle. So we would call this a 90-degree angle, right? It's going in the positive direction. So this is referred to as a right angle, right? So a right angle is a 90-degree angle, and it's 1/4 of a turn. Right. So then we also have what's called a straight angle. So a straight angle is 180 degrees, and it's 1/2 of a turn. Right? So to draw this, we would have something like this. Right, so it makes a line, right? Like a straight line, like straight angle, straight line. That's how helps me remember that. So this would be 180 degrees, right? And then two other terms that we use are acute acute angle and obtuse angle. Right? So an acute angle is an angle theta that's in between 0 degrees and 90 degrees. Right? An obtuse angle is an angle theta that's in between 90 degrees and 180 degrees. Right? And one thing you want to notice is I use the less than symbol, not less than or equal to, here in both cases, right? Because if theta was equal to 0 degrees, we wouldn't have an angle. If theta was equal to 90, then we'd have a right angle, right? So that's why we have to be in between, right? We're in between having no angle and a right angle. And then an obtuse angle, notice we can't be equal to 90, because if we're equal to 90, we'd be a right angle, not an obtuse angle. And if theta equaled 180 degrees, that would be a straight angle, right? So an obtuse angle is in between a right angle and a straight angle, right? So we can draw some diagrams here with these. So here's x, y. So basically we just need an angle in the first quadrant, and that would give me an acute angle. And then an obtuse angle would be an angle in the second quadrant, right? So like here, oops, meant to erase this, there. Right, so there's theta, right? So then have a couple of other terms that we can say here. So we can talk about what are called complementary and supplementary angles. So let's see, let me use a different color here. So two angles are, let's see, I think I'm going to run out of room. Let me just get rid of this 1/4 of a turn, right? Or I think maybe I can move it out of my way, right? So two angles are complementary if their sum of their measures is 90 degrees, right? Which is a right angle, right? And then two angles are what we call supplementary if their sum of their measure is 180 degrees, right? And we call this a straight angle, right, as defined above, right? And something that helps me remember complementary and supplementary and how they work is, remember the S's go together, right? So the straight angle, right, think of like a straight line, 180 degrees, and supplementary matches, the S in supplementary matches with the S in straight angle. So supplementary angles are angles that add up to be a straight angle, right? And then complementary, of course, would be the right angle option, right? So that's something that I use to help remember the difference. Right. So then we have some more terms to look at. So I promised this section was going to be a lot of terms. So a degree can be divided into 60 equal parts and these are called minutes. Right, so we can denote this as MIN, or with like one apostrophe, right, kind of mark, right? So it's like 60 minutes and an hour kind of thing, right? So we're thinking of a degree kind of like an hour, if you will, and then each minute then is divided into 60 equal parts called, and as you probably guessed, would be seconds, right? So we can denote this as SEC, or like two apostrophes, right? So then note that this is a similar relationship to hours, minutes, seconds, right? Just as I was describing, right? So makes it an easy way to estimate that, right? So now now that we've got some terms out of the way, we can do some examples. A couple examples here before moving on to the next objective. So example 1 is that we would like to convert 131 degrees, 12 minutes, 33 seconds to decimal degrees, round to 4 decimal places, right? So we want to convert the seconds and the minutes to degrees, right? So I think the easiest thing to do is to start with the seconds and convert that into a decimal part, using into minutes, right? So essentially, I want to take 33 seconds, and how many minutes is this, right? Because I'm thinking about 131 degrees, 12 minutes, and 33 seconds as being equal to 131 degrees plus 12 minutes plus 33 seconds, right? We can think about it in that fashion, right? So if I want to convert 33 seconds into minutes, right, I can just do a conversion like normal, right? So we can make what are called like unit fractions, right? So I can have 33 seconds, and I can put that over 1 if you wish, and then we want to multiply by a unit fraction. And a unit fraction is something that is equivalent to 1, and you just use a known statement, right? Like I know that 1 degree equals 60 minutes, and I know that 1 minute equals 60 seconds, right? So here, if I want to get rid of the seconds, I want seconds to be here. So this is my fact that I know. So there's 60 seconds and 1 minute, right? So when you take like seconds divided by seconds, those units cancel out, right? So if you want the units to cancel out, we want to have one on the top and one on the bottom. And notice what will be left is the minutes, which is what we're trying to convert to, right? So the unit you want to keep, you put on the top. The unit you want to get rid of, you put on the bottom, essentially, right? In this case, right? So then we just multiply straight across like we would multiply fractions. So here we would get, 33 times 1 over 1 times 60, and this would be minutes, which would be equal to, 33 over 60, which is equal to 0.55 minutes. Right? You know, an easy way to, you know, convert this. Let me grab my calculator. So if I just take, you know, 33 divided by 60, right, we can see it comes out to be exactly 0.55, right? So that's an exact answer. Right, because something else that's going to be important in this class is that you want to try to avoid, you know, getting an approximate answer and then using an approximate answer to get another approximate answer, because you're going to have what we call rounding error, right? So you want to have you don't want to approximate a round until the very end if at all possible, right? So this is exactly equal to 0.55 minutes, so we're good there, right? So essentially what I have right now is that you know, my original statement up here up top, this is equal to 131 degrees plus, and then I would have you know, 12.55 minutes, right? Because what I did is I converted this to be equal to 0.55 minutes. So then when I add it to this, right, that gives me 12.55 minutes, right? So this is what we have right now. So now, I mean, as you can imagine, I want to take these minutes and then convert it into degrees, right? So, you know, what I'm thinking right now is that I want to take 12.55 minutes and convert this into degrees. And then we'll be able to round to 4 decimal places, right? So, you know, we're starting with 12.55 minutes. I can put that over 1 if it's helpful, right? And then I want to multiply by a unit fraction. I'm going to want minutes on the top, or excuse me, the bottom, right? So that way these cancel. And then I would want degree on the top, right? Because that's the unit I want to get. So then we just need to fill in a statement, right, that equals 1, right? So we'd have 1 degree, 60 minutes, right? If it's not clear why this fraction is equal to 1, right, it's because 1 degree equals 60 minutes, right? So you're taking, you know, the same thing divided by the same thing. They're just written in a different form, right? Just like if I had, you know, 1 foot divided by 12 inches, right? 1 foot is equal to 12 inches. So each of these are equivalent to one another. They're just written in a different form. So that's why that's just equal to 1, right? It's important to note that, you know, anytime I multiply something by 1, multiplication property of 1 says that, you know, you get the same thing back, right? So in other words, I'm changing how these things look, right? I'm not changing the value, right, of the angle measurement, right? So now if I multiply straight across, right, what I end up getting is 12.55 degrees divided by 60, right? And you know, if you want to get a fraction, right, we could get our graphing calculator, right? So that wouldn't be a fraction because you don't want to have like a decimal inside of a fraction, right? So if I take 12.55 and divide it by 60, whoops, I need another 5. Right, and then I can hit this math button in this very first one. That'll take that answer and put it into a fraction. And nice thing about the TI calculators is that it'll always give me a reduced fraction as well, right? So basically what I found is that, let me get rid of this, is that this is equal to 251 over 1200 degrees, right? So then, in other words, you know, at this point, what I was working with is 131 degrees, 12.55 minutes, right? and I converted this and made this equal to be 131 and 251 over 12,000 degrees, which is approximately, so we want to round this to 4 decimal places, right? So if I look back at, look back at my calculator, right? 4 decimal places would be 2092, right? So we're just rounding that decimal part. So then what we would have is that this is approximately 131.2092 degrees. Right? So that would be our final answer, right? So not too crazy difficult, just just doing some conversions and being comfortable with the minutes and seconds form. All right, so example 2 is basically going backwards, right? We're starting out with this decimal form, decimal degrees, and we want to convert it into degrees, minutes, and seconds, right? So the way I like to think of it is I have 26.48 degrees, and I want to split this apart where I have degrees, minutes, and seconds. And the trick is, we have to put whole numbers on these boxes, right? So if you forget what whole numbers are the set of numbers 0, 1, 2, 3, and so forth, right? So there's no decimal part, right? So 26.48 degrees, right? It's pretty easy that I know this is going to be 26 degrees, right? So what I want to work with now essentially is I want to take this fractional part, 0.48 degrees, and I want to split this apart to be, minutes and seconds, right? So the first thing I would do is take 0.48 degrees and convert that into minutes. So if I want to put this into minutes, I can multiply by the unit fraction 60 minutes over 1 degree, right? So the degree would go away, and so we take 60 times 0.48, so we get 28.8 minutes, right? And you can double check that with your calculator. So this whole part, right, this 28, that's what's going to go here, right? Or in other words, here. So then what I want to do now is work with this fractional part, so 0.8 minutes, and set this equal to blank seconds, right? So we'd have 0.8 minutes over 1, multiply by unit fraction. I want seconds on the top, minutes on the bottom, right? So there are 60 seconds in 1 minute. So if I multiply straight across, right, the minutes cancel. We're going to get 0.8 times 60, which is 48 seconds, right? So 48 would go here, it would go here, and here, right? So this is the answer we're looking for, right? How to break that up. All right. So then objective 2 is to be able to find a radian measure, right? So we looked at degree measure, and I promised that there was a second way to find a measure of an angle. So that second way is using radians. So another type of angular measure that is typically better suited for applications in trigonometry and calculus is what we call radian measure, right? So this is typically a more convenient thing to use, right, than trig and calculus. So a central angle, so another term, is an angle with the vertex at the center of a circle, right? So it's going to come into play when we define radian measure. So A central angle that interprets an arc on the circle with length equal to the radius of the circle has a measure of 1 radian. Right? I'm going to draw some diagrams to help with these definitions here, right? To kind of put it in more perspective. So just to note something is that 1 radian equals, so we can say that as 1 radian or 1 rad, or we can say just 1, right? So in other words, radian measures carries no units. Right? In other words, radians are unitless. Right? So when you divide, like feet divided by feet, for example, that's going to give us a unitless measure, right? So after we look at maybe a picture here of what a radian is, then that'll make maybe a little more sense, right? But if you've taken like statistics before, another unitless measure is like a z-score, right? Maybe something that you've looked at before. Right? All right. So let's try to break this up. So if we pay attention to this a little bit, so a central angle is an angle with the vertex at the center of a circle, right? So essentially, if I have this circle on the xy axis, then if I have an angle in standard position that's inside this circle, right? Then if this is theta, then this would be a central angle, right? That's what that was trying to describe, right? So then, to help make this a little more sense about what a radian is, right? So we wrote down here that a central angle that intercepts an arc on the circle with length equal to the radius of the circle has a measure of 1 radian, right? So in other words, if this is 1 radian, then what would have to be true is this distance from here to here, right, would be the radius of the circle, right? So we'll just call that r. So this distance is r units. Then if this is 1 radian, what that means is that this arc length, so an arc length is a length of part of a circle, essentially, right? Like this is called an arc. Then if this arc length is also equal to r units, then that's what makes this 1 radius, or radian, right? So if you could imagine, if you want to have a circle or a central angle with, maybe we want alpha to be equal to 3 radians, right? Then what we would need to do is, start with my initial side, and then measure this distance from here to here, right? This would be r, and then we would just have to map out 3 r's, right? So if that's 1 r, then that would be 1 radian, and then go another r, there's another radian, and then go another r, there's another radian. So then if this goes through here, then this angle alpha would equal 3 radians, right? Because we were able to put three radiuses along the arc, right? So that's essentially what that definition means, right? So if I have an angle and I'm trying to figure out how many radians it is, then what I should do is take the arc length and divide it by the radius, right, to figure out how many radii fit in the arc, right? So like here, we would have 3r divided by r, which is just equal to 3, right? That's why it's 3 radians. Here, we would have r divided by r, which is just equal to 1, right? So it's 1 radian, right? So we want to take the arc length and then figure out how many radius fit in there, so we would divide by the distance of the radius, right? So let me come down here on the next page and do some more diagrams. So let me do this maybe a little more generic. Right, so if we just want to draw a central angle here, maybe something like this. Right, so there's my vertex, my initial side, and my terminal side here, right? Then we could let, this angle be, let's say, theta. Right? Then this is equal to s, right? We often use lowercase s for arc length, right? So we often use little r for radius, and s for the arc length, right? So if we're at a case where this distance here is r units, and the arc length happens to also be equal to r, then that would tell me theta equals 1 radian. Right? So just kind of how I walked through just a minute ago. Right? And then draw another diagram. So we need another central angle. Right, so let's say, this is, oops, let me change color. Say this is R, and we're able to map out, let's say, 2 radius, right? So in other words, S is equal to 2R. Then in this case, so this would also be, equal to R, right? Just still the radius of the circle. Then this, we could, let's say the angle is beta. Then beta would be equal to 2r divided by r, which is equal to 2, right? So it's 2 radians, right? So then the radian measure, so we have here the radian measure of a central angle theta subtended by an arc length s on a circle of radius r is given by the formula theta equals s divided by r, right? So in other words, we could say that a measurement in radians is the ratio of the arc length and radius, right? So that's what this equation is describing, right? Like a fraction is a ratio, right? We're comparing the arc length to the radius, right? And that's what gives us this angle measure, right? Radians. So to put this in perspective, 1 radian is approximately equal to 57.3 degrees. Right? You might think, how can we come up with that, and I can show you here in a minute, by asking the question, well, how many radians are in 1 full rotation? Right? Which we already said, which is 360 degrees. Right? So, in other words, if I have this diagram shown, so we need a circle, and then, maybe we could let this be angle theta, right? So if this is my initial side and also my terminal side, right? So I'm going all the way around, then this could be angle theta. Then the arc length, right, would be all the way around the circle, right? So in other words, that would be S, which would be equal to the circumference of the circle, right? So then we know, that this distance here is R, right? Because we use that for the radius of the circle. So the circumference of the circle, we can show that as 2 pi r, right? Circumference of a circle is pi times diameter, or 2 pi r, right? So you should have known that from, geometry or other math classes, right? So in other words, this S is equal to 2 pi r, right? That arc length. Right? So then, again, we're trying to find radians. So what we need to do is figure out how many radius measurements can fit inside the arc, right? It's a comparison. So the equation here is we want to take S divided by R, which would be equal to, so S, we could substitute this in for 2 pi r, right? And then divided by r. So what's going to happen is the r divided by r can simplify out, right? That's this is essentially, 2 pi times r over r, which is 2 pi times 1, right? Which leaves me with just 2 pi, right? And 2 pi is approximately equal to 6.28, right? Because pi is about 3.14, so double that is about double that's about 6.28, right? So in other words, 360 degrees, what we can learn here is that 360 degrees is equal to 2 pi, right? And if I divide both sides by 2, we can get that pi equals 180 degrees, right? So that's actually a statement that I can put here on this line. So it says the statement pi equals 180 degrees gives us a conversion factor to convert between degree measure and angular measure, right? So it's just a little easier since both sides are, multiple of 2, so we can just divide both sides by 2 and make this a little simpler, right? So this is a common statement that we'll use to convert, just like 12 inches is equal to 1 foot, right? So what I'd like to do is come over here and draw an XY plane, and just write down some things. Right, so we can think about this spot here as 0 degrees, which is also equal to 0 radians, and then we can also think of this spot as 2 pi, radians, which is equal to 360 degrees. Right? Right, so that's if I'm, starting and stopping here, right? So we could be at 0 degrees or actually go all the way around once, right? So then if I'm lined up here, right, this would be 90 degrees, which is equal to, so maybe it'd make more sense for me to do the straight angle first, right? So this would be 180 degrees, which we already just found that that's equivalent to pi radians, right? So if 180 degrees is equal to pi radians, then if I divide both sides by 2, that would give me 90 degrees equals pi over 2 radians, right? So then when I'm going from 180 to pi here, that would be, 270 degrees. So I'm basically adding these two things together, right? Adding another 90 degrees. So that would give me 3 pi over 2 radians, right? So we're starting to build this idea with angle measure on the XY plane, right? We're going to keep building on this. Right. So the statement pi equals 180 degrees gives us a conversion factor to convert between degree measure and the angular measure. We just looked at that. So then some frequently used angles are the following, right? So we're going to use these a lot. So 30 degrees is equivalent to pi over 6 radians. 60 degrees is equivalent to pi over 3. 45 degrees is equivalent to pi over 4, and 90 degrees is equivalent to pi over 2, right? And you can play around with this, using this conversion fact and show that, this would be the case, right? So like, if I take pi equals 180 degrees, divide both sides by 6, right? Then we get pi over 6 equals, and then 180 divided by 6 is 30, right? 30 degrees. So you can see how, I can come up with this statement, and you can, basically replicate that for the others pretty easily. Right. So then what we're ready to do now is convert from degrees to radians and radians to degrees, right? Practice some of that. So part A, we have the measure 300 degrees, and I want to convert this into radians. Right, so we can use the unit fraction idea like before. So if I start with 300 degrees, and you can put this over 1, but I'm not going to now, but you can feel free if it makes you feel a little more comfortable. So remember that we know that pi equals 180 degrees, right? So if I want the degrees to cancel, right, so again, if you want to put that over 1 and make you feel a little comfortable, go ahead. So if I want to convert into radians, I want radians on the top and degrees on the bottom, right? So that way the degrees cancel out. So I just need to fill in this statement. So we'd have pi radians equals 180 degrees. Oops, we don't need degree twice because I wrote it. So, the degrees will cancel. We just multiply straight across. So we get 300 pi over 180. And this would be, in radians. And then we can try to simplify this. So I can divide top and bottom by 60. So this gives me 5 pi over 3 radians. Right? And remember, it's perfectly fine if I left the radians off completely, right? Because radians are unitless, so it's okay to not write that, right? So then for part B, notice I have a negative angle measure, right? You can treat it the same way, right? We just have negative 70 degrees. If I want to go from degrees to radians, I'm going to put, pi over 180 degrees, right? So typically, when we have a radian measure, it's in terms of pi, right? So that's also a way to kind of help remember is if we want to go from degrees to radians, we want to introduce pi, so pi goes on the top, right? where you can see like here, like example 4, right? I'm starting out with pi over 18. I'm going from radians to degrees, and degrees typically is not in terms of pi, right? So we want to get rid of the pi, right? So how do I get rid of the pi? Put pi on the bottom, right? So to go from radians to degrees, you'd multiply by 180 degrees divided by pi, right? So that's another way that kind of helps me remember what to do as well, right? So just simplifying part B up here, this would give me, so the degrees will cancel. So this will give me negative 70 pi over 180. And then I can divide top and bottom by 10 to get negative 7 pi over 18. Right. So then for part A, I kind of set this one up already. Multiplying straight across. So the pi's will end up canceling. What we get is 180 degrees divided by 18, which is 10 degrees. Right? And then negative 4 pi thirds. Right, what we'd want to multiply by is 180 degrees over pi, which would equal negative 4 times 180 degrees divided by 3, which equals negative 240 degrees. Right, if you simplify that with your calculator, right? Because 180 divided by 3 is 60. 60 times 4, 240, right? All right, so we just finished the first 2 objectives. We're already an hour in. So I think I'm going to end the video here, and then I'll start a part B of this video to finish out these notes. All right.